Hello. First lecture for the class on statics. We're going to use the textbook by Hibbler, of course, just the statics part of it. And I'm going to cover the first few sections, chapter 1, general principles, and then force vectors. This will be a limited to 50 minutes recording, I believe. So let's get started. The first chapter is about some fundamentals, definition of mechanics. So it has several branches: rigid body mechanics, that'll be statics and dynamics. And then the formal body mechanics is the solid mechanics, strengths and materials in the undergraduate curriculum in fluid mechanics. Okay, so statics could be considered a particular case or special case of dynamics, where bodies are dressed or move with constant velocity. In dynamics, we study bodies that perform accelerated motion, although kinetics considered motion with constant velocity. So really, in statics, our systems will be stationary. But of course, depends on the reference frame. So you have, for example, an airplane in motion, and you perform a statics exercise inside, like simple case, what will be the weight of a carry-on as you hold it in your hand, with your hand, as the plane is flying. So I could give you examples on how fundamental to mechanical engineering education statics is. So you will be, the dynamics, the extension of it uses substantial amount of concepts on vector and forces and moments. And then for strengths and materials, and then other classes, fluid dynamics, as mentioned earlier, uses fundamentals from statics. So put it on top of your priority list, strong piece of advice, because if you don't have a good grasp of these fundamental concepts, you will be struggling along towards completing your engineering degree. So we in statics we use four basic quantities: length, time, mass, and force. So length, a measure of size or location. Time, of course, in statics, time is not irrelevant because things do not change. It's assumed stationary, system stationary. So, but dynamics, of course, is where time is very important aspect. And then mass is a measure of the resistance to acceleration of the body is visible in gravitational field, translates into the weight, and could be interaction of bodies between themselves, like celestial bodies or a spacecraft, as it moves interplanetary. Force, so the exertion of a body upon the other could be fluid over a solid body, or oftentimes we have the weight, gravity, action, but also the exerted force by a winch system, our own force, or just the pre-tension. Say have a stretch spring between two screws on a wood board. So yeah, the effect of the interaction between bodies is due to, or has as a result, forces. Okay, so some simplifications. We in the study of engineering, we work with models to make the math more manageable. So we have particles and bodies. So a particle could be an airplane flying, and you can assume the effect of like gravity and aerodynamic forces concentrated. One would be, I'm anticipating here, the center mass, and aerodynamic forces are concentrated in a point that's called pressure, center of pressure. Okay, so here's an example of two, what are these? The bungees acting upon a ring, and then probably a weight at the end, or could be three bungees connected that is not shown, but the ring could be assumed a particle. Okay, rigid bodies again, or could be of various shapes. I stop here for a moment. So in solving statics problems, drawing confidently rigid bodies with their constraints or freed from their constraints in drawings called free body diagrams is paramount. So, and in general, mechanical engineers communicate with sketches before you resort to CAD, to drafting package. You should be able to sketch, and in direct communications, or you can take photographs, scan them, in exchanging ideas. So before using computer to do your graphic figures, which always take as time, being able to draw sketches is essential. Everybody knows Leonardo da Vinci. Was not just painter. Actually, he lived his or made a living as an engineer, and being able to draw and sketch was very helpful to his endeavor, designing siege machines and defense systems, and then animatons for his patrons. So again, being able to draw, maybe with the help of a ruler. Just one last thing here. So don't be shy to draw half-page schematics as you solve problems. It probably comes with confidence. So if you want to hide something, you draw small. So again, draw big, draw. Use pencil and eraser. Remember that one too. Okay, so then forces. Really, all forces in nature are distributed. The concentrated force is an idealization, at least at the macro scale. So here's an example of a wheel on a steel rail. The contact between the two bodies is going to happen over a patch, which is small, over which the weight of the train, the part of the weight is delivered to the rail, is delivered to the weight of the car delivered to the wheel, and the wheel delivers that force to the rail. It's actually distributed over a small patch, so we assume that to be a concentrated force, and it's an okay approximation for most cases. Okay, so yeah, concentrated force. We'll discuss distributed forces a little bit later. We owe to Newton's these fundamental laws observed and never affirmed in nature. So there's no proof of them. Again, the three laws of motion. The first one, it says that a particle acted upon by forces that are in equilibrium will remain stationary or will move to constant velocity. Second law takes the case where there is a force on balance, and that results in the particle being accelerated. The velocity is increasing, or could be a deceleration case. So you're in a vehicle, you press the gas pedal, and if you exaggerate, you can feel the back of the seat pushing your own back. So yeah, that's a sign of, or when a plane takes off, you can tell that easier. So yeah, there's a force on balance. There's more friction force than is, say, air drag, opposing motion of the plane or the car, and then that results in an acceleration increase. Or when you slam the brakes, the friction force at the wheels is slowing down the vehicle, and you sense that there's a tendency for you to, move forward as you decelerate again. In extreme cases, you lock the seat belt due to that tendency of the body again to continue the rectilinear motion as the car slows as you slam the brake. Okay, in the third law of motion, it says that two forces in action between particles, or the interaction between forces stated between two particles induce an action or reaction force. A force by itself is not possible. You always have, you push with a finger a book to slide on a horizontal surface of a desk. There is a force is delivered to the book, but also the book delivers a force to your finger. In case of a vehicle that is moving at constant speed, we have a balance, an equilibrium between the friction force of the driving wheels, and we have air drag and rolling resistance. So those are in equilibrium, have constant velocity. So yeah, the aerodynamic force is the effect of the mass of air that flow again or act against the windshield, the rest of the car body. And so there, the aspect is a bit more subtle, but still we have action and reaction, the interaction. And we talk in statics, solid particles. So yeah, they exist in pair. A force by itself is not possible. They're always going to be in pair, action and reaction. Okay, and in addition to the three laws of motion, which the student should memorize, should be able to recite, there is the law of gravitational attraction. The anecdote was Newton sitting under an apple tree and an apple falling and realizing that the apple has fallen because the earth was pulling the apple towards the center of the earth. So the law of gravitational attraction is stated, Newton's law of gravitation, as shown here, equation 1, 2. So the force between that apple and the earth, or between the earth and the apple, the earth is also pulled towards the apple, but of course the mass difference is, as we know, substantial. So yeah, it can be evaluated with this formula. So we have the universal constant of gravitation. It was measured experimentally, and these are the mass of two bodies, and this is the distance between their center of mass. Here it talks about particles, so we're assuming them to be, dimensionless, and this will be if it sets the distance between particles will be the distance between their. We haven't talked about center of mass, center of gravity, but this is what this R is. Okay, so this constant has been determined experimentally first by a scientist named Cavendish, if I recall correctly the name, at any two particles, like you have two watermelons on a table, they attract each other with a force, but because mass are so small and this constant being so likewise small, 10 to the negative 12, these forces are minute. However, Earth having such a big mass makes this force significant. Everybody knows the moon is a smaller celestial body, and the objects, astronauts, their rovers, we're about to go back to the moon after 50 plus years. They're attracted with a lower force. That's why the big ellipse that they can make on the moon, and everything else, and the lack of atmosphere. So not enough gravitational pull. The Earth never developed an atmosphere, and Mars too doesn't have a um, you know atmosphere compared to that on the Earth. I'm not talking oxygen here. I'm just talking about um, the density of the gas that formed the Mars atmosphere. It had to do with the mass of the Mars being less than that of the Earth. Okay, so weight is this force where one of the masses is the mass of the Earth, and the radius r, it'll be, if you're the Earth's surface, that'll be the radius of the Earth. Of course, it's not constant. Earth is not a perfect sphere to begin with, and then the density of the Earth fluctuates. So the there is a change in gravitational acceleration to gravity as you move from place to place on Earth. Okay, so yeah, the product gravitational constant, universal constant of gravitation, gravitation, times the mass of the Earth times or divided by radius of the Earth squared gives you the acceleration to gravity, and the weight of bodies at the Earth's surface can be calculated with this formula where G has it depends, I said, from place to place, but we work with some standard values. Here it shows an astronaut doing spacewalking. You can see the Earth curvature. So it says here its weight is diminished since she's far removed from the gravitational field of the Earth. You experience massless, weightlessness on the International Space Station, or during orbiting of space vehicles, like was the space shuttle. But that's for other reasons. So in order for the satellites, International Space Station, to remain on the orbit, it has to have a tangential velocity. It has to move around the Earth at certain speed. If that speed is decreased, the satellite, the space station, is deorbiting, and it falls back on the Earth. So there is indeed it's less gravitational pull on the orbit, but not by much. Space station, I think it's less than 300 miles above the Earth's surface, and we can even calculate what acceleration of gravity is where the International Space Station is. Okay, so yeah, moving forward, units and measures. We have the International System units, SI, with length in meter times second, mass in kilogram, and force is a derived unit using Newton's law. So all these now are defined, I think, including mass. The Avogadro number is a constant included with SI units, I believe. So the latest definitions of weight might just go in terms of a perfectly sized sphere that has a certain number of molecules, and it corresponds to a mass of a kilogram. It might be anecdotal what I'm saying, but in any case, so for a good while, mass was just a block of alloy hold in certain lab conditions, and the meter for a while was just a piece of a rod made of platinum and iridium, hold at steady temperature. But now it's defined based on some atomic phenomenon, like a wavelength, well, as that mass, and then time likewise. Anyway, so these are fundamental units. Force is derived, I said, using Newton's law. And we stay in Newton's law without a proportional constant. So as you can see, force, mass times acceleration. And then in terms of gravitational acceleration due to gravity, gravitational constant, am I saying the right thing? So we use universal constant of gravitation and gravitational constant. Yes, at the Earth's surface, this is the value it will be working with. So weight will be m times g, with g 9.81 meters per second squared. In use customer units, the fundamental are length, time, and force, and mass is defined using Newton's second law. In terms of the other three, for SI units, we have, like I said, meter, second, kilogram, that is length, time, and mass, and force is a derived unit using Newton's second law. Okay, so in order for Newton's second law to be defined in terms of mass times acceleration, we use for mass in US customer units, English units, mass in slugs. So sometimes students ask, is it pound mass? Or we're not using pound mass here. We're just using pounds as measure of force, and masses in use, or mass in use customer units will be in units of slug. And so one slug has a weight of 32.2 pounds, and stated here, and acceleration to gravity in US customer units has 32.2 feet per second squared. Okay, so going between the two systems, we have pound slug foot, and the corresponding, so one pound would be 4.448 newtons. One slug is 14.59 kilograms, and 1 foot is 0.3048 meters. And we sometimes use inches. So 1 inch is 25.4 millimeters. That will be for measurements, strength materials, design machine elements. We're going to use inch instead. Okay, there are some prefixes here that go with expressing measures in various units. So kilogram is the only one that use kilogram, is too small. Unit, same Pascal for pressure, force per unit area, is a small value. And in circuits, you're going to see that farad is too big value. Anyway, so mega, kilo, and milli will be more commonly seen in our analysis. Giga, micro, possibly micrometer, micro-inch, to define precision measurements in fabrication, and nano, less our business. You can see how, what is it, 10 to power -9. Okay. So in order to distinguish the different units, we use dots between themselves. He gives an example here, meter second instead of millisecond. That will be a big confusion. So with a dot, well, that confusion is eliminated. And then this discussion is about using prefixes on the numerator rather than denominator. So instead of Newton per millimeter, recommends kilonewtons per meter. And what is this? Meter per milligram should be megameter per kilogram. Okay. And then when doing calculations, we're concerned about dimensional homogeneity. You may have seen this in physics classes. They provide one mean to, partially check if the accuracy of formulae or used in physics and mechanics. You should be concerned about dimensional homogeneity in your calculations. Okay. And then for significant figures, we'll be using calculators. So save to the calculator memory the intermediate results, and then when you report, results will be 2 or 3 digits, which are practical. So if you're to measure length in meters, for example, you can go up to, a millimeter is 1/1000th of a meter, but we can do measurements up to microns, so rather commonly. Okay, and grams and milligrams versus the kilogram, which is the fundamental unit. Report with 3 significant digits your results. Using calculators, don't write down intermediate results, just save them to the memory and retrieve them from there, continue calculation. Okay. All right. So, I highlighted this in color other than light green. So it says attending lecture, reading the book, and studying the example problems is helpful. But the most effective way of learning mechanics, and in general, for any class, is by solving problems. Not reading solved problems, not watching myself or other instructor solving problems on the board or projecting problems step by step, revealing the steps progressively from PowerPoint. Actually, that's not my style of going with students over problem, but rather you're there, you draw, you calculate, you verify the correctness of the answer by checking, do they look reasonable? Are my formulae homogeneous in terms of units, as we discussed earlier? So dimensional homogeneity is one immediate way of verifying results. Okay, there's a summary of what was taught here in this first chapter. Again, Newton's 3 laws of motion should be memorized. You verify how many minutes of recording I have. 28. Okay, I can move forward. There's some sample problems here, converting from kilometer per hour to meter per second, and then to foot per second, and then pound second. That's pound second in slug per foot, the power 3 into SI units. I will be doing this as a part of the more involved analysis. And as we will be meeting face to face, we're going to go over some problems. Moving to the next section, chapter 2, that is on scalars and vectors. And I'm sure you've seen this before. So being able to operate or solve problems, apply concepts from statics and from other, from dynamics, from solid mechanics, fluid mechanics, being able to work with scalar units and vector units is, again, very important. So a scalar, it's a number, positive, that's associated with a physical quantity. So just magnitude. One example is length, or our example will be length, mass, and time. Sometimes time could be negative. It could be taken negative, but definitely we cannot have a negative mass. Although that could be a case, we have a missing mass and we say it's a negative mass, and length or distance could be, from origin going in reverse. So it says any positive or negative. Okay, so I'm not contradicting what the author says. Could be also negative. And then vectors is a physical quantity that, in addition to magnitude, has a direction. So magnitude alone is not enough for the analysis. In more general cases, we can deal with linear, linear in the sense that their configuration is on the line, and the direction, the sense of direction are common to all vector measures in question. So, but in general, a vector has direction, and this is a two-dimensional case. This is the scale of the vector. You see the angle 20 degrees. I don't quite like the fact that the angle is not oriented. We like to measure angles counterclockwise, and in as much as possible, it is the trigonometric orientation of angles. And from the x-axis or parallel to x-axis, I'll be. You'll see me. I have that preference. It simplifies our life, reduces the chance of making errors. So yeah, this is the line that draws the direction of the vector. The line, we have the tail, we have the head. So the vector orientations from O to P. It's at an angle of 20 degrees, and it's in the, if we're to show the y-axis, in the first quadrant. By taking this angle, up to 90 degrees, it can go past 90 degrees. Actually, it could go negative 2. So in print, you see a vectors as boldface letter, and in handwriting we draw a line or an arrow, sometimes just a line for convenience. Yeah, for magnitude, we're going to just skip the line. Magnitude of the vector refers to magnitude, or in print it will be a italic letter for the vector magnitude. Okay, so we have operations with vectors. You can have multiplication and division. Multiplication, or rather division, is multiplying with a less than 1 scalar. Multiplication, that scalar is greater than 1. So you see here initial vector, and 2 scalar 2 times the vector makes it twice as long. Take the vector, multiply -1, essentially you flip the vector. It changed the sense direction. And if you multiply the vector with a number that is negative and less than 1, flipped it, and you reduce its magnitude to half the 0.5. Okay, and then we have addition and subtractions of 2 vectors, and could be of more than 2. So it takes the case of 2 vectors discussed first. So we have them shown here, A and B. Assume them to be sliding, so you're extending them until the tails coincide. And we can use the parallelogram law, or we can use the triangle law. So by the way, in Newton's Principia, he stated vector addition as a law, but since it was downgraded to just vector algebra. Anyway, so I have the 2 vectors tail to tail. The sum of the 2 vectors would be the diagonal of the parallelogram. That's why the parallelogram law that is formed. You complete the drawing, so you draw parallel to A through the head of B. You draw parallel to B at the head of A, and you complete a parallelogram, and then the diagonal of parallelogram, it's the resultant vector, and the tail of the resultant vector, it's at the the common tail of A and B. With the triangle rule, we go the other way. So we hold A fixed, we slide B such that they are head to tail. They're shown here, head to tail, and then we complete the triangle. So the resultant vector has the tail coincident with A and that head coincident with B. This triangle rule. You can do it the other way. Vector addition is commutative, so A plus B vectors is the same as B plus A vectors. So for B plus A, you hold B, you move A tail to head of B, and then you complete the triangle. Using geometry, you need to know some angles, some more information in addition to magnitude. You can actually calculate the magnitude of the resultant as well as its orientation. So here it appears that the resultant is horizontal, but doesn't mean that all cases will be such. So you can, the diagonal of the parallelogram or the third side of this triangle could be other than horizontal. I mentioned a special case where vectors are collinear, and here their orientation is understood is x-axis or y-axis or some direction. You just put them head to tail, and then you complete the. It's like a collapse case of a triangle rule, maybe. Subtraction of vectors is the addition. The vector that gets subtracted, it's turned into the negative of the vector. So essentially, you flip it. So you have the original vectors A and B. We subtract B from A. We flip B, and it gets us, or we're building the parallelogram, a parallelogram law or a triangle law, where B again is flipped. The tail becomes the head, and head becomes the tail. Okay. Forces. So forces are vectors of prime concern in statics in general. So we can have, like in dynamics, you'll see velocities or acceleration being added or are vectors, and vector algebra applied to these type of vectors. It's common, but to us, forces, and later on we'll also see moments. Those are vectors too, that we need to do calculations with them. So gives examples of two concurrent. So the tension in these chains, and there's the third one, the hook, the chains extending their line intersect somewhere at this point. So question is, say, if I know these two forces, F1, F2, what is the resultant force, which is really the tension in the cable, or it could go the other way. So I know the resultant force. What are the two components over the direction of these? Could be ropes or likewise cables. So that's the matter of resolving force into components. Okay, so things that we seen for vectors in general here apply to forces. How do you get the resultant? Here is no longer, the resultant is no longer a horizontal vector. So yeah, you complete a parallelogram, you draw the missing sides, you draw the diagonal, or you draw the triangle, and using other information about the initial two vectors f1, f2, you can calculate the magnitude of the resultant, and you can calculate the angle that is made with some convenient direction, maybe the horizontal or could be the vertical line. Okay. And then the other sometimes is more involved than adding vectors. So resolving a force into components, and not the orthogonal components is the problem of when these directions are other than orthogonal, like you see here. So I know the weight of this drum. That will translate into the effect of the whole system upon the scan lever. And question is, what is the tension into these two cables that support the drum? So a practical example. Okay, so here we have the direction U and V. We have the component of this force as Fu and Fv. I stop here for just a moment. Different authors of similar books on statics and dynamics, they had a preference for U and I. You may see me doing that also. We're going to use different type of lines, maybe solid for the existing vectors and dashed for the resultant. He's actually doing this. He's using blue color for the resultant and black color for the initial, for the vectors, because it makes a difference. You may have 1, 2, 3 forces acting. What is their resultant? Or you can have just the original and their resultant, or the initial vector and the components. Okay, let's see, 42, not too many minutes of, I'm limited to only 50 minutes of recording. So finding the components of a force given the direction, how do you resolve it along the axis? Looks like I got, what is this? I don't know, something. Okay, so yeah, we have directions of interest U and V. How are we going to resolve F into the U and V components? Well, we complete a parallelogram. So draw the direction V, or a line parallel to V, through the head of F, and draw a line parallel to U to the head of F. So we complete the parallelogram, and then we have the two components, or you can use a triangle. So that would be a matter of just drawing U, or rather V, I'm sorry, or line parallel to kind of. So it starts with what? You extend this line, you draw it here, and you complete a triangle. So yes, a result, and of course, knowledge of geometry, like what is the angle between U and V and between U and F, or maybe everything about it, relevant direction, like a horizontal here, U appears to be a horizontal, will help to extract the magnitudes and their directions. So if U is horizontal, you know the angle between V. Using law of sines or law of cosines or both, you can find the components. So resolving F into components over two directions other than orthogonal. Addition of more than two forces. So we can group them into pairs. So our first pair, and then this was the next one, and then we get the in-between resultant, and then so forth. So here we have three vectors, F1, F2, and F3. We add F1 and F2 using parallelogram rule. So we get the resultant F1 plus F2, and then we add F1 plus F2 with F3. So we build another parallelogram, and we got the final resultant of the three. And some practical case. Looks like there's a chain here in the printed copy, or a PDF. Yeah, printed copy. I think the I'm just checking, as good quality as in the PDF in the printed copy. Okay, so a summary of important points here, and then procedure for the analysis. This is trigonometry, which using the law of sine, law of cosine. So I warmly recommend you to memorize this. It's not first time you're seeing the law of cosine, law of sines. Usually students have, my experience, difficulty recognizing or implementing writing a law of cosine. Again, you start with a helpful notation of side lengths and angles. So C is C, B and B, A and A. Opposing angle and side, the same notation, or could be A and alpha, B and beta, C and gamma. And it looks like Pythagorean theorem, but has this additional term. So one way of remembering the law of cosines. So it's a negative, and we have the product of these two, A and B, and then your cosine of the angle between the two. Okay, one way of memorizing. And then with the law of sines, there's the A and A, B and B, C and C. Sometimes it's written with sine on top, sine A over A. Anyway, so these are two equations. And of course, you can repeat the law of cosines for A equals square root of and B equals square root of by circular or permutation of terms. You can write the other two forms. Again, you apply it depending on what's available in what you want to calculate. All right, some sample problems. And here we have this first sample problem. So two forces, some angles, and we want to find the resultant. So you recognize that in parallelogram, sum of angles are equal to 360. So these are two triangles that are mirrored. Are they mirrored? No, they are identical triangles. Anyway, so knowledge that in a parallelogram the sum of angles equals 360. It's helpful in adding information to the problem and resorting to the law of cosines, or maybe law of cosines, depending on what is known, to find the resultant magnitude and also the angle. So if we know theta, angle measured from a horizontal will be just theta plus 15 degrees of the angle that was originally given. And some other sample problems. And then chapter problems we'll do of them. And so as Hiller says, doing problems on your own rather than watching others solving problems is key to mastering statics. I'll repeat it as often as I could. Statics is a very important subject for mechanical engineering undergraduate instruction. So I'm going to stop here, first recording, and there will be a second one for coplanar forces using orthogonal reference frames. So recording stops here, and I'll continue. All right, so I'm continuing this recording. I want to cover section 2.4, addition of systems of coplanar forces. So you'll see using a Cartesian orthogonal frame x, y. Okay, so if we have a vector, force vector F, and we know its orientation given by orient and angle theta. Again, my preference is for angles being measured counterclockwise from the x-axis, so that will invariably make these two components, the projection of f vector over x and y, magnitude of f cosine theta, and for the vertical axis, magnitude of f times sine theta. I've seen this in some books. I'm not very fond of this way of specifying the orientation of the vector with the small slope triangle, where you know A and B. You can calculate C, or maybe all three are given. So oftentimes it's Pythagorean numbers, or A and B are Pythagorean numbers. So in that case, the projection over x-axis is the magnitude F times A over C. So what would be A over C? That's going to be the angle formed here. I'm trying to, between the horizontal and the C, or at the direction of the vector. And then the y component, you need to pay attention now. So there's the minus sign accompanied by a drawing, that a projection, the y direction or the y-axis is a negative direction of y, it is downwards. And that's going to be, so again, negative magnitude of F times B over C. So B over C, that's going to be, okay, that's going to be the, we can take a cosine of this angle or sine of this other angle. Again, I have a preference for this form, and I have a preference for measuring angles counterclockwise and from the x-axis. If you follow the two rules, so again, measure theta from the x and measure it counterclockwise, then these will hold true irrespective of magnitude of theta. So pay attention here. If this vector F is in the second quadrant, appears where it will have a negative x component, you don't need to put a negative there. It will be the magnitude of the angle theta that takes care of that negative of the projection. Okay, and likewise for F. So if, say, the vector is in the third or fourth quadrant with a negative y projection, you don't need to put a number, a minus there. If the angle is measured from the x-axis, the magnitude of it will take care of making sine negative. Okay. Okay, so the projections are likewise oriented, so you need to, again, use signs, appropriate signs when reporting them. And then a word about writing magnitude. So italic will be, and you can see the negative to complement or the orientation. Yes, but italic means that the vector is just the magnitude of the vector. So italic F, magnitude of F, italic for Y, that's the Fy, that's the magnitude of it. Okay. So here it says, how similar written near vector errors indicate the magnitude of the vector, which is always a positive quantity. Yes, but what about Fy? Is this a projection? So it's not a magnitude of projection, it's a sign value. I was a bit hesitant because of that reason. Anyway, so that's one way you report the x and y components, separate values, but you can also include them into this vector format. So you calculate the way shown, with the angle or the little triangle, slope triangle, fx and fy, and then you state this vector equation. So you multiply the magnitudes of the projection x and y with their signs, negative or positive, with the unit vector. So if you've seen this before in physics, so x-axis unit vector associated is I, magnitude is 1, has the positive direction of x-axis. J has magnitude of 1, has it's oriented positive direction in the positive direction of y. And you state it as shown. So fxi, scalar product, plus fy times j. I said scalar product, no, multiplication between a scalar and a vector. So that's better. if we have systems of multiple vector forces in particular, there are intersecting at a or converge at a point. What is it? Coplanar. So acting at the same point, and that's the origin of the XY frame. You write them in this Cartesian format. So you calculate the corresponding x and y projections with the proper signs, and then you can add vectors. You'll see we have a preference for this. It's more systematic, less prone to error. So you can get the resultant by just adding the x-axis component, the multiplier, to the I unit vector, and then you do separate addition of the multipliers of the j unit vector, and so those two, and that will be the resultant. If you want the magnitude, use Pythagorean theorem. You just take the square root of frx squared plus fry squared, and so you take the square root, and it will be the magnitude. Sometimes showing, I would say if x is stated, that's the x-axis, if y is stated is the y-axis, but adding this information to show that positive of x is horizontal to the right and positive of y is vertical up. It might be helpful to avoid any possible confusions. So in general, using the sum sign, you can you can say that the projection of the resultant over the x-axis, sum of the projection of the individual vector forces, and for the y-axis, the resultant projection is sum of the y components. And I anticipated, but here it's stated for the more general case. So again, equation 2-1. So the resultant, the magnitude of the resultant, you apply Pythagorean theorem, so you take the square root of the sum of the squared components. For the angle at which the resultant is oriented about the x-axis, so you use the tangent or arctangent of the angle. So you take the ratio of the y component and divide by the x component. And here I'm seeing what appears to be a absolute value or module. The angle could be other than, so if this reaction is in the second, third quadrant, you need to use judgment. So you look at these signs. If they are both positive, fry is positive, frx is positive, the resultant is the first quadrant. If y is negative, x is positive, we're in the third quadrant. If both are so if both are negative, then it's the third quadrant, both projection negative. The x is positive, y negative is the fourth quadrant. The x component or projection is of the resultant is negative, y positive, or in the second quadrant. So again, use judgment when you report this angle. Look at the magnitudes or at the signs, yes, of these projection of the resultant. Okay, so there are some there are a number of problems here, and I warmly recommend you to study them on your own. We'll be practicing these in class, using or going over some of the problems. I'll try to make a selection of what I consider to be representative problems. There are too many of them to cover them in class. And he has some with a star, meaning that one, those ones do not have an answer at the back of the book. He's good at this. Most of his problems are like this one does not have an answer at the back of the book. So most of his problems have an answer at the back of the book. All right, so this was the second part of this recording. I'm going to stop here, and yeah, this will be the first lecture.